In this lesson, we will look at some of the techniques to estimate canopy fuel loadings. We will cover a few of the techniques to estimate canopy fuel loadings or biomass, available canopy fuel loading for crown fire, crown bulk density, and crown base height. Crown fires are a concern to many managers because they exhibit higher rates of spread than surface fires, produce more smoke per acre, have longer lasting ecological effects, have greater threats to firefighter and public safety, and have increased risks of property loss. A variety of modeling systems have been developed to link surface fire behavior to crown fire behavior, such as Nexus, FFE-FBS, and crown fire initiation and spread. Each of these models integrates separate equations to predict surface fire behavior, surface fire transition into a crown fire, and crown fire behavior. The use of such models can help managers develop silviculture prescriptions to reduce the threat of crown fires, prioritize treatment areas, assess current crown fire hazard, and predict the effects of a crown fire under different scenarios. It is outside the scope of this class to discuss all the individual fire models available for us. However, all of these models have several common canopy characteristics which need to be measured or estimated. Before we get into this lesson, I want to review several definitions. First, the term total canopy biomass, or canopy fuel loading, will refer to the total amount of biomass or fuel in the canopy fuel stratum. The available canopy fuels loading is the part of the canopy that can burn in the flaming front. Typically, this is all the foliage and some part of the 1-hour fuels. Canopy bulk density is the dry weight of available canopy fuels per unit canopy volume, and the canopy base height is the distance from the ground surface to the base of the canopy fuel stratum. Another important terminology difference is that the term canopy refers to a stand level property, and the term crown refers to a tree property. Now let's move on to quantifying. There are 3 broad methods used to estimate canopy fuel properties: instrument-based approaches, inventory-based approaches, and heuristic-based approaches. In this section, we will focus on inventory-based approaches. The most popular method for estimating crown biomass is the use of allometric equations. Many studies have been conducted to predict crown biomass using allometric equations. Michaelian and Korzik in 1997 summarized equations for 65 tree species. In their review, they used the equation M equals ADB, where M is the oven-dry weight of the biomass, D is the diameter at breast height, and A and B are parameters. They suggest that the use of this equation is a good balance between accurate predictions and low data requirements because it only requires diameter at breast height. These equations provide an alternative to destructive sampling for the purpose of developing local equations. However, the user has to rely on estimates developed from other sites. Although this program is concerning, several approaches have been suggested to counteract this. First, you can simply find the closest geographic site, or you could use several equations to estimate the range of biomass. And last, you could generate biomass equations with various equations and fit a new equation to the generated data. Also, crown biomass equations are not available for all tree species, size classes, and stand conditions, so many times this method is not practical, as noted in Keen et al. 2005. These equations only use diameter at breast height to predict canopy biomass, while other equations may include additional variables such as tree height. Other variables have been shown to be statistically significant, but their inclusion does not necessarily lead to a higher R2 or a decrease in prediction error. In this example, we will calculate the total canopy biomass for a Douglas fir stand in northern Idaho using the equation from Tur, Michaelian, and Korsigan 1997, and a dataset of DBH from a 1/10 acre plot. First, we must find an appropriate equation to use. The table above shows that only one equation exists to predict the total canopy biomass, labeled as AB in the table. We now will generate our equation. The equation will have the form m equals 0.0808 times dBH raised to the 2.5282. In this table, you can see that we converted our dBH from inches to centimeters and calculated the total canopy biomass for each tree in the plot. We then summed the total biomass for every tree on the plot. Now we want to calculate the total biomass per hectare. To do this, we can multiply the plot's biomass by 10 since we collected this data on a 10th acre plot. Then we convert this number from kilograms per acre to kilograms per hectare by multiplying by 0.404. We have now estimated the total canopy biomass for our stand. Note that for this example, we used an equation developed by Marshall and Wang 1995. Most fuels management applications use equations developed by Brown 1978 and by Brown et al. 1977. The table you pull these equations from will tell you the source of the data. Here's a subset of the Brown 1978 equations. Notice that the equations calculate total biomass as well as the proportion of foliage. These are the equations, or the lookup tables below should be used in the canopy fuels assignment. Using the table on the previous slide, let's walk through an example for a 10-inch ponderosa pine. A quick alternative to using the allometric equation is presented in Brown 1978, which uses lookup tables such as these published in Brown et al. 1977. Part of the table is shown here. Notice that the table will lose some accuracy since it only has weights for whole ponderosa pine with a diameter of 10 inches. First, find the ponderosa pine on the table labeled PP, then go down until you reach the 10-inch dBH line. You will see that a 10-inch ponderosa pine has a crown weight of 171 pounds. Again, these lookup tables are from Brown et al. 1977. These tables are shown in Appendix 3. Let's stick with our 10-inch ponderosa pine for this example. Remember that the total crown weight was 171 pounds. If we look at this table, we see that the foliage makes up 33% of the total crown weight, which is equal to 56.4 pounds. Now let's calculate the percentage of total biomass that is in the 1-hour canopy fuels. Again, we will continue with our ponderosa pine example. In this case, we see that 0.04% of the total canopy biomass is in 1-hour fuels. Remember that our total canopy biomass was 171 pounds. Thus, we have a total of 6.8 pounds of 1-hour fuels, as this is 0.04% of 171 pounds. Now let's calculate the 10-hour fuels for the same data example. In this case, you see that about 38% of the total crown biomass is captured in 10-hour fuels. Thus, our 10-hour fuel loading is about 65 pounds. In this table, you see the proportion of total biomass that is between 1 to 3 inches in the 100-hour fuels. For our 10-inch ponderosa pine, you can see that is equal to 22% or 37.6 pounds. Lastly, let's estimate the percentage of total biomass that is greater than 3 inches. In this case, we see that it is 0.03% or 5 pounds. Here are our final numbers for our hypothetical ponderosa pine tree. Now let's assume that we know there are 150 ponderosa pine trees with a diameter of 10 inches per acre. Convert this estimate into tons per acre by dividing by 2,000, as this is the typical units for stand level data. And when we do this calculation, we get 12.8 tons per acre of canopy fuels. Remember that the available canopy fuels is the part of the canopy that can burn in the flaming front, typically the foliage, which is 1-hour fuels, and some of the 10-hour fuels. Now we have calculated the total canopy biomass using allometric equations. Again, we will use the same ponderosa pine forest with 150 10-inch trees on it. You can see I added a row to our table called available fuel loading because we decided that all foliage in 1-hour fuels would be counted in the available fuels. I simply moved these values over. For the 10-hour fuels, I divided our estimate in half and then added that to the column. I then crossed out all the other fuel values and added the numbers up, multiplied by 150 to get a stand average, and then divided by 2,000 to get tons per acre. You can see that our available fuel loading estimate is 7.2 tons per acre. I am going to switch gears here to another set of equations. We are going to look at the allometric equations developed by Cruz et al. 2003. These equations are somewhat different in that they directly estimate available fuel loading. Cruz et al. 2003 calls this term canopy fuel loading, or CFL. You can see that this equation is developed for 4 different ecosystems. The equations themselves predict the natural log of canopy fuel loading, so you will have to take the inverse of the natural log to solve for the fuel loading. This equation has 2 input parameters, basal area and trees per hectare. It also has 3 coefficients, B0, B1, and B2, which are dependent upon the ecosystem. For this equation, you can see we need to calculate the basal area in square meters per hectare and the trees per hectare. We will use a dataset from northern Arizona ponderosa pine forest to do these calculations. Note that the trees per hectare is equal to 272 and the basal area is 33.2 meters squared per hectare. Let's go over the calculations. We will begin by writing out the full equation. Next, add our numbers into the equation and calculate the right-hand side of the equation. At this point, you should have natural log of CFL equals 0.05. Now remove the natural log from the left-hand side of the equation, and the final step is to convert it to kilograms per hectare from kilograms per meter squared. Your final answer should be 10,521 kilograms per hectare. Now, how accurate are all these predictions? Well, Reinhardt et al. 2006 published a paper which compares several indirect methods for estimating canopy fuels to direct measurements of canopy fuels on 5 sites throughout the western U.S. I would like to cover several of their findings regarding available canopy fuel loadings. This study compared the allometric equations developed by Brown, 1978, and the regression equations developed by Cruz et al. 2003, and a set of adjustments or multiplication factors based on crown class. The results of this study suggested that both the Brown and Cruz et al. Equations had poor correlations to direct measurements. The average difference between the predicted and observed data was 0.7 and 0.56 kilogram per meter squared respectively. Due to error associated with these estimates, the authors suggest that there may be potential in using the adjusted allometric equations as an alternative, although they admit that much more work is needed in this field. Keep this in mind as we move forward and in your use of these equations, because they are not infallible. The multiplication factors that were developed by Reinhardt et al. 2006 are shown here. You can see that these multiplication factors are divided by both species and site. Thus, if you were to use one of the multiplication factors, you would have to select the correct location that best represents your data. Reinhardt et al. 2003 states that the error of the predictions was only off by 0.11 kilograms per meter squared, which is why they suggest that this may be a good alternative to the other approaches. At the very least, these results suggest that crown position may be an important factor in estimating canopy fuel loadings. I want you to use these adjustments in your loading calculations in this lesson assignment. Let's look at how to utilize the adjustment factors. If we return to our stand of ponderosa pine in northern Arizona, you will recall that there was an available fuel loading of 7.2 tons per acre and that each tree had an available fuel loading of 95.7 pounds. Assume that all our trees are classified as codominant trees. In this case, we can look up an adjustment factor from the table I just showed. Let's use 0.2 for ponderosa pine in Flagstaff, Arizona. Now we can apply that factor to each tree. Thus, instead of each tree having 95.7 pounds of fuel, they will have 19.4 pounds. Now, multiply this by the trees per acre and divide by 2,000 to convert to tons per acre, and we get 1.44 tons per acre of available fuel. In this case, since all our trees were classified as codominant, we could have also simply applied the factor to our original estimate of 7.2 tons per acre. Many times we are conducting fuels inventory to design and/or to evaluate a treatment's effects. To help show you how you can use these equations and tables to help determine additions to the surface fuels during a thinning operation, we will go over the example problem in the Brown et al. 1977 paper you read. The first step is for us to collect and summarize tree inventory data. This summary should be done by listing trees per acre by 1-inch diameter classes by species. Here is a list of the trees we expect to cut. Note that this is a partial cut in a grand fir and larch stand in northern Idaho. The next step in the process is to select the correct weight tables for each tree and to multiply the number of trees per acre by the weight. For pre-commercial thinning and trampling from harvest activities, Brown recommends using the tables for a 6-inch merchantable tip diameter when the tree will be left in place. For trees over 6 inches, only crown and bowl material less than 6 inches will be counted. We then want to estimate slash weight defect using this equation. We will not cover how to estimate defect in this class, but you can find methods for this in many forest measurement textbooks. Here is a summary of our example slash weight. Finally, we can add up our expected slash weight from cutting, trampling, and breakage. You can see from this calculation that we will expect to leave about 27.8 tons per acre of slash after the harvest. If you have an estimate of the existing downed woody debris, you can add this as well to estimate a total tons per acre after the harvest. In this case, it will be equal to about 45.8 tons per acre. Lastly, I want to briefly touch on biomass estimates using instruments. Typically, when we use instrument-based approaches, we are attempting to estimate the gap fraction of the site. The gap fraction is the proportion of the sky visible when viewed from below the canopy. We can use the gap fraction to estimate leaf area index, then assume that biomass of branches supporting foliage is proportional to the foliage biomass. Using this assumption, we can estimate amount of canopy biomass as well as the canopy bulk density. We will talk more about canopy bulk density in the next lecture. A common method in instrument-based approaches is to use a gap fraction, as I mentioned on the last slide. This can be estimated using several approaches. Two of the most common approaches are digital imagery from the ground and from remote sensing. Here is a hemispherical photo of a Douglas fir lodgepole pine stand. When we analyze this stand, we see that the gap fraction is equal to 0.53. The inverse of the gap fraction is the percent cover of the stand. In this case, it is equal to 47%. We will not cover all the calculations for this stand from this image. However, from knowing the species and percent cover, we can now estimate the foliage biomass to be 0.9 kilograms per meter squared and the total canopy fuel load to be 1.19 kilograms per meter squared. Keep this technique in mind for another viable option in your fieldwork. The downside is these special lenses tend to be fairly expensive, and you need a computer program to help you analyze the images.